Thanks, Dr. Shah, for this organization, and good afternoon, ladies and gentlemen. As already announced today, I will give you first talk about state of the art, some challenges and application in model order reduction, computational science, and engineering. Maybe I don't have to spend much of the time about convincing you concerning the important development of computational science and engineering in the last few years, but what is clear is that we are witnessing a growing importance in terms of multi-physics modeling and also multiple scales in terms of space and time. We have many research partners from industry and clinics are demanding for more and more efficient computational tools for real-time computing, but also repetitive computational environment for optimization in iterative methods, and also the capability to increase the complexity related with the parametric formulation, as well as also the capability to quantify uncertainty. And the perspective that I'm going to provide today is a computational collaboration rather than competition between what is high-performance computing and reduced order methods. Here you have some example of parametric problem, parametric flows in industry or biomedical application, where you have parametric shapes for domains, but also different flow regime. This means also different dimensionless number, like the well-known Reynolds number, for example. I would like to acknowledge that the results that I'm presenting today are, of course, in collaboration with my group, also with some national and international partners. And we are a group of numerical analysis in Trieste, the International School for Advanced Studies. And we are basically devoted to methodological developments for numerical methods. And our aim is to enhance the exploitation of computational science and engineering, where in fields where at the moment maybe there is still little exploitation. Today I will focus mostly on computational fluid dynamics, but of course fluid mechanics is our central physics of interest, but you may think that what I'm introducing is also for multi-physics and a coupled setting. And there are several potential applications in different fields of engineering characterized by fluids. I would like to give you, before starting with a more deep overview and motivation, also some coming from some application and some projects related with some industrial application, as well as in biomedicine and related with environmental sciences. The first one is are examples taken from some cooperative project at the local level in Trieste. Sophia was a project where we had to optimize the shape of a motor yacht, but the design was to be carried out not in calm water, but in non-calm sea condition. And here you have a repetitive computational environment for shape optimization. Another project, Prelica, for example, was related with the redesign of the propeller blades in order to reduce the underwater hydroacoustic noise. And also in this case, we have a repetitive computational environment for the optimization of the single propeller blades. If we want to go to a more complex level, we have also to deal with complex fluid models or fluid phenomena that should be taken into consideration. And for example, here we have some project in cooperation with Fincantieri, who is one of the biggest shipyard in the Mediterranean Sea. And in this case, you can see that we are looking at data-driven model order reduction for optimization. The first case, the shape optimization of the bulbous bow of a cruise ship or the hull itself. In the second case, again, the design of propeller blades. In this case, we have to take into account not only the hydroacoustic noise, but also the fact that we want to avoid some complex phenomena like erosion and cavitation phenomena. For this kind of problem, the model order reduction will be given by data-driven approach. and the computational environment is repetitive. And in this case, for example, we don't even have access to the full order solution and situation, but the company is providing us. Other development could be, for example, in cardiovascular flows. And in this case, we can think to data-driven reduce order method for that patient-specific data. So we are incorporating clinical data inside our model in order to bridge the gap between the numerical solution and experimental clinical data. We want to guarantee some important speed up for this. And the idea is that we may use, again, data-driven model order reduction. This is even more important if we think that we don't have a perfect knowledge of the boundary condition at the inlet or at the outflow. And maybe we may want to use a flow control setting where the control function is in the outflow. In this case, sometimes we have data, experimental data, for some section of our arterial flows, and we want to reduce the difference between experimental data and numerical solution. We want to guarantee a certain speed up for this kind of simulation because we would like that this could happen in real time, and this means order of seconds or some minutes, few minutes, I would say. Another field of interest with the recent development is related with the development of a reduced order method for atmospheric and ocean flows. So geophysical flows and weather forecasts. In this case, we are also facing some reduction technique for turbulence. And in this case, I mentioned, for example, RGD simulation. But we had to guarantee an important speed up of order of magnitude compared with the full order. And also we have to guarantee this for longer time prediction. This is a recent field of interest for us. A more classical one was the one related, for example, with the flow control in water or airs, for example, the pollution dispersion of pollutant, for example, in the Gulf of Trieste, close to Sissa. And in this case, the parameterization could come from wind intensity and wind direction. For example, we want to understand how a potential accident into a commercial port could impact, for example, a naturalistic area like the one represented here close to the Miramare Castle. These are just examples that they want to provide you a motivation about repetitive computational environment, parametric computing. And in terms of development of model order reduction, I would like just to spend a few seconds on these slides where we have the two levels of our problem, the full order and the reduced order level. Full order is characterized by a classic discretization technique, high fidelity solution, to be accelerated. And the reduced order method is acting as an accelerator. In the first case, there are discretization techniques that you are already expert, like finite element, finite volume, finite difference, spectral element method. The reduced order level is guaranteeing us an external layer to the problem because we are providing a surrogate solution for the state solution U. We have another layer for our problem, but the most important thing is that we have to deal into an efficient way with parameterization. And another important thing is that at the end, we will have an input-output relationship and like a black box between the new value of a parameter and then the state solution, but carrying out a surrogate, a reduced order solution. This input-output evaluation has been a great opportunity recently because we may replace this with also modern algorithm based on automatic learning. So what before was mostly a projection method, now it can be seen as an opportunity in order to include and incorporate many recent developments related with machine learning, for example. If you are interested in going more deeply inside this methodology, I would like to point out that there is a 3 volumes handbook in the framework of European Union cooperation in science and technology, the MORNET action, Model Reduction Network, where there is this open access book edited by the Gruiter. So you can freely download the PDF for this book on the official web site of the press, the Gruiter. if you are interested in this other topic, mostly related with non-linear and time-dependent flow, there is also this Acta Numerica review paper with Iane Staven and Cecilia Pagliantini, written last year as an update of the former book with Iane Staven, and a more recent book edited by Cyan Press with Giovanni Stabile and Francesco Ballarini about model order reduction for computational fluid dynamics. The methodology is bringing also a technology development perspective, because we want to go to real-time computing visualization thanks to offline-online computational paradigm. This means that we may have a splitting between what is high-performance computing, offline computing, to build our snapshot for the selective value of the parameter. This is very expensive and time-demanding. And so this is the preparation step for POD, reduced basis, principal generalized decomposition. The online part can go to more common devices like laptop, desktop, but also smartphone or tablet. It's extremely fast. It's a real-time input-output evaluation, like the black box. And you may have even an intermediate perspective where everything is done by web, thanks to a web browser, so we can have a computational web server in between. And this is also the source of investigation for an European Research Council proof of concept, Argos project, where we are developing this computational web server in order to be able to develop apps for each problem of interest in industry or in some applied science setting. And this framework is allowing also a better exposition of reduced order modeling to HPC data science, but also to modern technologies like digital twin, or to some paradigms like in Industry 4.0, like SMACT, social mobile analytics, cloud computing, Internet of Things, or in additive manufacturing. In order to be able to spread this methodology, we have also to take care of the development of the updated and most modern methodologies that have been developed in the last few years. And to do that, we have, thanks to a consolidator grant of the European Research Council, the project ROM, CFD, we have developed several open source software library. They are freely available at this web address, matlab.cissa.it/CSE software. And there are several different libraries. Ithaca, in real-time and advanced computational application, is providing an interface, model reduction for finite volume, spectral element methods, and discontinuous Galerki. And the reference full order libraries are OpenFOAM or Nectar. Otherwise, we have the finite element tool, which is based on the project Phoenix on finite element. And this is used also for educational and training activities. Then we have some development for the web server, Argos and Atlas. And we have also several other libraries that have been developed mostly for data-driven model order reduction, like EasyRB, or PyDMD for dynamic model composition, and several other service tools in order to manage parametrization, geometrical morphing, and also a technique in order to reduce the parametric space, for example, on Athena. So there are several other libraries that can be combined in order to reach your goal. I would like just to spend again a few words about the fact that if digital twin for us is now one of the central topic, is a new umbrella for computational science and engineering, I would like to say that if we can better exploit HPC and data science for digital twins, I think that there is an important potential provided by reduced order methods, and of course by automatic learning. And we would like to incorporate also in this framework better tools for uncertainty quantification, because this is in any case crucial above all if we are dealing with data as a companion for our mathematical and physical models. This is why we do prefer to talk about big models instead of big data, because we would like to incorporate also our mathematical and physical modeling. This is just a perspective of integration of different fields to better exploit HPC also in context where at the moment there is still little development. But with the reduced order method, we have a more sustainable framework for scientific computing, because we can reuse computations. So we will have energy savings, but we will have also reduced computational time. And this means also reduced computational resources. So this is for sure one of the modern perspective in CSC. I would like also to spend few words from the origin, so where we were before this development, which has an integration also with automatic learning, for example. So the basic idea for a reduced order modeling approach is that we have a full order problem, parametric one. We select some parameters value, so some configuration of our system, and we compute the fidelity solution. Then we may decide if we can have, for example, here a POD approach or a more reduced basis approach. A POD approach is more expensive because we have a correlation matrix to build, and then we have to compute eigenvalues, eigenvectors, and we have to rely on the POD modes. On the reduced basis side, we have the global approximation function, and then we may need a Gram-Schmidt orthonormalization. The Galerkin projection may be relaxed a bit in terms concerning the complexity of our problems, if we have to incorporate also problems that are data-driven and so on. So we will rely a little bit on some variants for the online step and the reduced order formulation, but the state of the art is reported here. In terms of challenges and frontier for this approach, I would like to introduce, for example, in computational fluid dynamics, some of the open fronts that are under investigation at the moment. Of course, a better geometric parametrization, the capability to increase the Reynolds number to go to more and more complex industrial flows, the capability of having accuracy, pressure approximation and recovery, the capability of coupling, nonlinear coupling in multiphysics, some automatic learning development, turbulence modeling, which is Reynolds average and Navier-Stokes equation, large simulation, for example, the capability to reduce and simplify parameter space, because also in this case, the parameter space will affect the complexity of our problem. But also the capability to solve inverse problem like flow control and data assimilation. And a good numerical methods, the full order and at the reduced order level should be also be able to detect in a parametric setting the loss of uniqueness of the solution. And so, for example, to detect bifurcation, branching of solution in nonlinear PDEs. And then, of course, the stability of this solution. So these are just few, let's say, elements that I'm providing on the table for these kind of approaches and development. Historically, let's say, reduced order methods in fluid dynamics was first developed for finite element and then for finite volume, so increasing Reynolds number. This was a different choice for the full order methods. The key problem is related always with the stabilization. Stabilization is an issue of the full order, but also the reduced order level for fluid dynamics. We have to fulfill an equivalency subcondition, and we had, of course, to enrich our spaces properly to fulfill this in sup. And then we had also, of course, stabilization technique, like, for example, the one that I will recall in the following. But I would like also to say that the new complexity is characterized by the fact that we want to incorporate turbulence, or the fact that we have more and more complex application. So we may even think to go to compressible flows, bifurcations, multiphysics. So also not only finite volume, but also spectral methods or discontinuous Galerkin could be option for our solutions at the full order level to be then reduced. The stabilization, as I mentioned, is an important issue for also for the reduced order method. And I would like historically just to recall what has been done for reduce order method based on finite elements. So we had to fulfill an in-sub condition, and we had to fulfill some finite element pair, like the Taylor would one for velocity and pressure. And in order to do that, we had also to enrich the velocity space with some additional velocity, the so-called supermiser. But this was not enough. When we have transport-dominated problem, we needed also to introduce some stream up with Petrogall-Erkin technique. And this is due also at the reduced order level, but in this sense, we had to develop offline online stabilization technique. So this is a state of the art for finite element. And I just recall that in sup condition for the reduced order methods also is parametric, is built on a reduced order level, so different level with respect to the full order one, but there is always the saddle point structure and formulation for our problem. If we want to go to finite volume, for example, here, we can see that we want to rebuild the velocity and pressure fields. And here, for example, we focus more on time-dependent flows. We know that a standard approach for ROM would bring a lack of accuracy, and we need again to introduce some proper stabilization. The reduced order level for this kind of problem where we want to build to rebuild our modes for velocity and pressure, these are A and B vector, we had for example this equivalent structure, which is a dynamical system where A and B are our unknown. So this is a state of the art, for example, for a time-dependent formulation. In this case, we may use finite volume. The idea is that then for the stabilization, we rely on a supermiser approach or a Poisson pressure equation. The PP approach is just replacing the continuity with the Poisson pressure equation. But at the end, you have this dynamical system again. For the supermiser, we are just enriching the velocity fields, and there is a locking condition, because the cardinality of the supermiser should be greater or equal than the number of pressure snapshot. And this is, let's say, state of the art for these approaches. And if you are interested, this work with Giovanni Stabile on computer and fluids is reporting this state of the art. If we want to introduce some turbulence modeling for this setting, of course, we have two possible options for reduced order method. Or we go to a purely data-driven approach, or we introduce some physics-based data-driven approach. And I will introduce both, and then I will introduce a tiered option, which is a mix of the two. So the idea is that, again, the state of the art with the POD Galerkin ROMs for this kind of problem is not giving enough accuracy. And the first step that we may do is to use a sort of data-enhanced variational multiscale ROMs. This was one of our inspiration. This less inspired idea is aims at reintroducing the contribution of the neglected modes in ROM. And the idea is that we have some correction, the velocity correction and the velocity and pressure correction for supermiser or Poisson pressure equation respectively. Here we see that we have the same structure as before for the dynamical system, but now we have some correction, tau u and tau p. The state of the art is in this Journal Computational Physics 2023 for this idea. Of course, the physics-based, data-driven, is considering projection for some quantity, but for example, if you are introducing a turbulence model with a large eddy viscosity, what we may do is to develop the viscosity extracting the POD modes. And so the idea is that the coefficient of this development for modes, the G coefficient, will not be given by projection, but will be given by a data-driven approach. In this case, we use a regression technique based on a neural network. Otherwise, we may have, for example, a radial basis function. And the idea, as you can see here, is that now the two dynamical systems are bringing as unknown three different vectors, A and B, velocity and pressure, and then G for the eddy viscosity. And the state of the art for this approach is in this paper, Computational Physics 2020. The final, here you can see that we may have an hybrid approach, like reported here, where we have both something which is data-driven, and then we may have the correction terms. If we had a look at the results of these hybrid data-driven ROMs, are better in agreement with the full order methods. And in this case, this is what we are using now for the solution of some problem in order to have a better accuracy. And if you're interested, in cooperation also with Trainiliesco, Virginia Tech, the final results are in this Journal of Applied Mathematics and Computation for this year. Before going on from turbulence to some more complex configuration, I would like also to mention the problem of geometrical parametrization, because we have parametric domains to deal. Usually we use freeform deformation or radial basis function. So we have a shape morphing, and the lattice of points is made up by our parameters. And these are several examples in naval engineering, but also in automotive. But there are also examples where we don't have a freeform deformation, but we have a reconstruction, like in this case of geometries coming from cardiovascular flows. And for geometrical parametrization, we need also to be able to build this non-smooth benchmark. This is the Ahmed body, which is a non-smooth aerodynamic design, I would say. But we need, in any case, to be able to manage also this into a parametric setting. So another important problem is that we have meshes that should be guarantee quality also under small deformation for the shape. And the idea is that, of course, we have also to compare our numerical discretization maybe with some experimental data in order to guarantee the industrial level this kind of accuracy. Now, if we want to put together turbulence and geometrical parametrization, the approach is reported here. So we have basically the same structure. We go with this incompressible Navier-Stokes equation formulation, and we build over this Reynolds average Navier-Stokes equation. So again, you see here that we have an eddy viscosity, basically nu T to build. The approach for this kind of problem, if we want to introduce also geometry and not only physical parametrization, will increase some complexity of our parametrization on one side, and then also on our data-driven approach. So the idea is that if we stick on this dynamical system using one of the two approaches, supermiser or Poisson pressure equation, the unknowns are always the coefficient of velocity and pressure development. The idea is that the viscosity and the geometry is included in this neural network mapping. This regression map is taking as an input not only the velocity coefficient, but also the geometry, for example. In the output, we have the coefficient of the development of our eddy viscosity. So the approach is quite standard, but the complexity at the input layer is a bit more involved. This was a work also in cooperation with Volkswagen in the framework of ARIA projects. So in this case, we have viscosity, turbulence with runs, and then we have geometry. Here we see that the Ahmed body is parameterized in this angle. There is an analogy with this backstep changing this angle too. And if you want to have a look at some results for this kind of problem, first things is that we have a quite a fast convergence over the decay of the POD modes for velocity, pressure, in this case also at the viscosity. And then the training and the test function for the neural network is quite standard. But what you can see is that the dimension of this basis function are quite reduced in terms of cardinality. If we want to go to a slightly more complex configuration, we can decide to go to compressible fields. So in this setting, we will have also the energy equation, because we have thermodynamic, we have a varying density field. We may use average Navier-Stokes equation with Favre formulation. And we can have different cases. The one based on physical parametrization, where the Reynolds number is varying of several order of magnitude, and we have an important Mach number. Otherwise, we have geometrical parametrization on this NACA airfoil, and again, we fix the Mach number to 0.5, where compressibility is present, but then we have high Reynolds number. If we compare these two cases, we can say that performances are quite equivalent. So here you have the physical parameterization. And what you can see, we have, of course, we have also energy in this setting. And we have a viscosity. So we have one more equation to study in the decay of the POD modes. And if you see these physical results with the Reynolds average Navier-Stokes equation and a big variation of Reynolds number is equivalent to this one. And in this case, we have geometrical parameterization. This geometrical parameterization is including the deformation of the NECA airfoil at a high Reynolds number and Mach number 0.5. But you see that the dimension and the performances are quite the same. So this was, let's say, the framework, completing a bit the increasing complexity for CFD. Now we may have also some further application of machine learning for this kind of problem. And the idea is that, of course, machine learning could, so more generally, artificial intelligence could enhance classical ROM technique. And I would like to mention the fact that you have seen how to use a POD neural network in reduced order modeling, but for example, you could use autoencoder, especially if you have transport-dominated problem. You may use also autoencoder for dimensionality reduction, manifold learning, and also some technique to reduce and simplify the parameter space. If you are interested, there you have some work recently, Journal Scientific Computing 2023. The first one is on Canva, accepted on Canva now, computer method application. And then a CMAME paper for last year on computational method applied mechanics engineering. Our approach is more physics informed oriented. So we are developing a software library, open source software library called PINA for a Python package for differential equation based on physics informed neural network, where we are taking into account not only the governing equation, the state equation in the loss function, but also taking into account the structure of the operators like symmetry. And we are also developing a deep operator learning, which usually is data-driven, but also a possibility to make it physics-informed. And if you are interested in this kind of work, like to mention the work on computer and mathematics with application with Nicola Demo and Maria Strazzullo. Our more, let's say, recent approaches and tests are based on the use of generative models for reduction technique. So not only for the generation of solution for our parametric time-dependent problems, but we would like to incorporate also some other enhancement in order to have a good management of computational meshes for the structural properties. Very important also to incorporate having an integrated approach for uncertainty quantification, given the fact that we are using a probabilistic approach in generative models. So this is just a very brief mention about what we are doing at the moment. Another important field that we are developing is related on the fact that we are compressing big neural network architecture. So we want to introduce a parametric reduction, for example, for convolutional neural network, for image recognition, image reconstruction. And this is one of the approach into a work with Laura Meneghetti and Nicola Demo, which just appeared on Applied Intelligence. We do think that this is important in order to have good performances and also reduce space memory also for neural network application. But of course, what we are doing at the moment, mostly for our problem related with PD, is a physics informed approach, like you can see here. And I don't know how many minutes I still have before discussion. I kindly ask the chairman.
So you have 11 minutes. So like last 5 minutes you would like to keep. So around 5-6 minutes you can take more.
Thank you. I would like just to give you some example of what of projects that are using the state of the art that I introduced in order to apply as a proof of concept this methodology. One was a project is related with urban air pollution. And this is quite standard in terms of methodological development and application, but the complexity is coming also on the fact that it's a real world problem. So this is a data-driven problem and data assimilation problem, because we have several data from pollution emission, and they are collected in experimental devices that are spread all over a city or a campus. First example was the main campus of the University of Bologna, and the second example you'll see is the city of Győr in Hungary. This is a cooperation with the University of Széchenyi Istava University in Hungary. And for this kind of problem, we are using classical hyper-reduction technique and dynamic, so discrete empirical interpolation. But here you have an example of the input in the right-hand side that we have to incorporate in a non-affine way in our problem. This is 4 different sensors that in time are collecting air pollution data. So the idea is that we have our dynamical system that it's basically the one that you saw before. But the idea is that we have to manage in the first case with 40,000 cells, in the second case with 3 million cells. And so we have a real traffic model with urban pollution depending on time. And this is a proof of concept, because to face this kind of problem, we need model reduction, but we need also techniques that are able to incorporate experimental data in our problem, in this case in the right-hand side that you see here. But we have to guarantee some accuracy, and at the same time also some computational performances that are close to the real-time one. Another important problem was related, for example, with some phenomena with the fast transient dynamics. And this is, for example, related with explosion and damages that could occur after explosion due to pressure wave. This work was in cooperation with the Joint Research Center of the European Union in ISPRA. And this is also related, of course, with risk evaluation, damage estimation. And the idea was to start from the state of the art after the simulation that has been done for the Beirut explosion in 2020 in the port. And we have used some buildings, like the one of the SISTA campus, in order to better understand this fast transient dynamic. And for this kind of approach, even if the state of the art was still in place, we had to enhance a little bit the state of the art of our methodology. And so we were using non-linear, non-intrusive, so data-driven ROM, and we were combining POD with autoencoders for some compression, and in order to enhance the pressure reconstruction and calculation for such a fast transient dynamic. If we compare with this approach with the classic one, we have a sort of enhancement. You see in the figure on the right that the blue one is the new performance with the enhanced methodology, also with the POD and autoencoder, compared with the classical POD. But in this case, also we are recovering a more accurate pressure fields in the reconstruction of the pressure trajectories. So this was an example of how also a state of the art should be somehow enhanced for some specific problem like the one characterized by this fast transient dynamic. And concern more complex application, I would like just to recall one of the example that I did as a motivational one at the beginning. And just to recall again the redesign of the propeller blade in order to reduce the underwater noise and also some cavitation and erosion phenomena. Of course, as you see, an optimization process is quite involved because it's taking into account of offline, online computation for model reduction, preparation, parametrization, and then also the formation and even an optimization process since it's related with a shape design. And things are quite involved, but model order reduction is able to keep this iterative methodology under a certain threshold in terms of computational time. And so having this kind of approach, which is more appealing for industry also, since for each iteration, things are happening in a limited amount of time. Of course, things are also complex because we have to manage geometry, and we have the blade parameterization and the mesh deformation that should be taken into consideration. And at the same time, also the standard ROM sometimes is even too expensive compared with a quick and fast tool. So the idea, for example, is that we may have a fast ROM at the beginning as an evaluation on as evaluation purposes, and then we may rely on a standard ROM for verification and comparison for accuracy and quality of physical solution with a full order. But this is just an example of a real world problem where the state of the art of computational fluid dynamics has been incorporated with a data-driven setting. And then, of course, we may guarantee some improvement in the performances, in the efficiency, for example, of the propeller blade in their use, and also at an acceptable error level compared with the expectation of results. So I would stop here, not to go over time, and I would like to thank you for your attention.
So thank you very much for the wonderful talk. Yeah, we have time to take 2-3 quick questions. So yeah, we have one question. It seems that people from SHG, it seems that people still use FOM for computation. Why do you think that people still prefer FOM over ROM, and disadvantages of reduced order models? Yeah.
Well, we need a full order for the snapshot, for our basis function, for our starting point, in order to introduce complex phenomena and also the right energy level in our problem. And I think that this is something where we can have physics. I would stick with physics, where we need to relax a bit this, because we need some performances that otherwise would not be acceptable, or where we don't have a perfect knowledge, we may combine better, maybe some reduced order modeling with some automatic learning. But if we have physics available, knowledge, and also solution, I would try to continue combining these two levels.
Yeah. Thank you. Then we have next question. Are there guaranteed priori error estimates for reduced order models?
Yes, for simple problems, for simple parameterization, yes. But when you go to complex geometries, to complex parameterization, and also to very complex model like the one incorporating turbulence, we have the same problem that also the full order community is facing, basically. So we have basically in computational fluid dynamics, we have problems in certifying solution for long time simulation and higher Reynolds number. So there are some barriers that are affecting not only ROMs, but also FOMs, I would say.
Thank you. And we'll take one more last question, that how do you determine the optimal number of snapshots of the high fidelity model, or what are the main aspects to select these snapshots? Yeah.
Well, in literature, you may have several options. Some have more theoretical one, more classic one, also for a limited number of parameters. Some are more involved, like the studies that has been proposed in the last few years on greedy algorithms. Now I think that it's time that maybe to see for some combination of some generative models and so on. So maybe now it's time to compare performances. But the optimal number of snapshot in a classical sense could be decided according the accuracy that you may want to reach, thanks to a posteriori error estimation based on residuals and stability factor. Of course, these for simpler parametric PDs problem.
And thank you. I think there are more questions, but we would like to now move to the next speaker. So yeah, but you can always contact Professor Rozza if you are, or refer to his work, which he showed during his presentation. And yeah, I would like to thank you once again, Professor Rozza, for his time and talk. And yeah, we'll now move to the